All right, here we are with the first short answer question from this set of 5 FRQ problems. All right, on every set of 5 FRQ problems for any mock FRQ that's meant to emulate the AP Physics 1 exam, there will be 2 short answer questions. And the only thing we know about the 2 short answer questions is that they're going to cover material not already covered on the other FRQ problems. All right, so on this short answer question, it looks like we have a mass spring system. All right, what I see here is a block attached to a spring, and it looks like there are 3 points marked on a horizontal surface. I'm going to go out on a limb and say that this looks like it's probably the equilibrium position because it says everything over here is positive, and it seems as though we are currently holding this block at its amplitude from the equilibrium. So that said, it looks like there's currently a force acting in this direction on the block by the hand and a force acting in this direction on the block by the spring wanting to restore back to the equilibrium. The question says block 1 is at rest on a horizontal surface and is connected to a wall by an ideal spring. Friction between block 1 and the surface is negligible. Block 1 is held at rest at point A to the left of point B, which is the equilibrium. There we go. Affirming that point B is the equilibrium. Block 1 is then released. Block 1 is then released and allowed to oscillate. So I imagine it's going to be going back and forth between A and C. Sometime later, block 1 is momentarily at rest at C. I think it means momentarily at rest because that's just where it's going to be changing position, suggesting that this is also the amplitude, the farthest point from equilibrium we're going to reach. Consider the positive horizontal direction to be toward the right. A says, the dot below represents block 1 just after it is released. On the dot, draw an arrow indicating the direction of the net force exerted on the block just after it is released. The arrow should start on and point away from the dot. I really like how they coach you a little bit on how to draw the arrow. Any net force arrow should start on the dot and be pointing away from the dot in the direction of the net force. So let's consider the question a little bit looking at the figure. We can assume that right now, as we're holding the block here, it's currently has 0 net force. But if we let go, the restoring force of the spring is going to push the block towards the equilibrium. All right? A restoring force always points towards the equilibrium. So if the block is at A, the restoring force is pointing towards equilibrium. And if the block is at C, the restoring force is pointing to the left towards equilibrium. But the moment we release our hand from this block here, the restoring force is going to be pointing towards the equilibrium, and that is the direction of our net force. So all we have to do here is we have to go ahead and draw a vector arrow. And it's not really that important the size of the vector arrow, as long as it's starting on the dot and pointing to the right, the positive x direction from the dot. This is 1 point. Now this question is worth 7 total points, and that was an easy first point. All right. Continuing on, it looks like we have a graph here, and this graph is going to be plotting the velocity of the block as it's oscillating with respect to time. So this is velocity on the y-axis, and this is time on the x-axis. The question says, after the block has been oscillating on the table, a motion detector is turned on, and the velocity of block 1 as a function of time is measured and plotted in a graph. The students correctly draw a best fit curve that represents the collected data as shown above. So these dots represent collected data, and then the actual line you see represents the best fit sinusoidal curve. Part B says that a student looking at the graph of velocity as a function of time makes the following claim. The motion sensor was turned on when the block was at point A and was moving to the left. All right, guys, this point where it says the motion sensor was turned on, it's just saying at time 0, when we start collecting data, where was the block? Well, what we know about the block at the point when we turn on our motion sensor is that it had maximum amount of negative velocity. It had a maximum amount of negative velocity. And so I know that if this is 0 velocity, the velocity at this point was negative, and it looks like it's hitting a peak here. So that said, where on this figure can we expect our velocity to be at a maximum? And when I say maximum, I'm talking about the magnitude of the velocity. So whether it's a peak or a trough on this velocity versus time graph. That said, the equilibrium position should be the point in which velocity is at its min or maxes, okay? because when we hit A or we hit C, this is a point in when we're actually changing direction. And when we change direction, our velocity is momentarily at 0. All right. That said, B is going to be the point when we're hitting our largest positive or largest negative, depending on how you're looking at it, where the magnitude of velocity is maximum. Now, if the block is currently moving in the positive direction, that's when we're going to have a peak on our graph. If the block is moving to the left, that's when we're going to have a trough, or like the opposite of a peak on the graph. So it looks like we have a trough here. So our object must have been at point B. This must be point B, and it must be moving to the left. All right. To label this graph a little bit more, we also know that this is point B moving to the right. This is point B again moving to the left. This is point B again moving to the right. And this is point B again moving to the left. Now let's see, what was it that the student was saying again? The motion sensor was turned on when the block was at point A and was moving to the left? Well, we just decided that the block was in fact at point B when the motion sensor was turned on, but indeed it was moving to the left. So that means the student was right about one thing, but wrong about one other part of their statement. B goes on to say, does the data in the graph support the student's claim about the location and the direction of the block's motion when the motion sensor was turned on? Okay, so for any incorrect claims, if any, state the correct position and or direction of motion. Justify your answer. I'm going to tell you how you get the points on this problem because there are 3 points to get on this part of the FRQ. First off, we have to state that the student was correct about the fact that the block was moving to the left. The student was correct to say that the block was moving to the left. Good. We also need to give some justification here. Because, you might want to put a comma here, because velocity is negative and as a vector must be pointing left or pointing negative if you prefer. Good. That's a really great statement for stating the claim that the student was correct about and then justifying that. That's 1 point. Now, how do we get the other points? Well, we're going to have to go ahead and state what it was that the student was incorrect about. Then make a correct statement, a correction to their statement, and justify. In that, we will get the other 2 points. So the student was, so you might want to also write, the student was incorrect in stating that the block was at point A. So there we are stating what the student was incorrect about. We want to make sure that we basically restate what they said. And let's say that we are affirming that it was incorrect. All right. Then we want to make a correct statement. Okay, so my correct statement might be the block was at point B when the motion sensor was turned on. So this is a correct statement, but we're missing only one last thing: justification for our correction. Okay, so our correct statement was that the block was at point B when the motion sensor was turned on, but our justification is going to look something like this. Because we are at a maximum in the magnitude of our velocity, which only occurs at equilibrium. Now you can pad this, you can say, which only occurs at equilibrium for an object that is in simple harmonic motion. But this will do for getting you that second and third point. Now let's go ahead and move on. You're going to notice that there's a figure here that has a second block. I think that's a little bit of a formatting issue because that's supposed to apply to part C. So let's go ahead and read part C and then take a look at that figure with the second block. Part C says, block 1 is stopped, and again, block 1 is held at rest at point A. A second identical block, there's that second block, is placed at point B, the equilibrium position. Block 1 is released from rest and then collides and sticks to block 2. After the collision, the two blocks oscillate together on the spring. On the graph below, sketch a curve to indicate the new velocity as a function of time of the two blocks after the collision. For reference, the dashed curve represents the student's best fit curve of the velocity as a function of time described in part B. Okay, so what we're seeing here is this graph is the same as the graph we were working with up here. This is the graph for when there is no second block. All right, but now we're going to have to compare a new graph for what happens if we do collide with the second block at that equilibrium position and draw it, basically superimpose it over this graph so that we can see the differences between the two. That said, let's talk about what might happen here, because we know we're going to go ahead and reset this by holding on to it right here, and then we're going to release it, and the block is going to restore back to equilibrium, collide with block 2, and then continue moving to likely the very same position C. But let's talk about it. What are the aspects of this graph that we might want to change? Okay, because if you're looking at a sinusoidal graph, there's basically two things that you're concerned about. What is the amplitude? The amplitude is here. What is the amplitude? And what is the period? The period is here. Okay, so the amplitude is the maximum distance from the x-axis, and the period is the distance between each peak. So those are the two things that we can really change, but let's talk about what they mean, because the amplitude is basically how big is the magnitude of the max velocity. Well, in this case, it's a certain amount, right? We don't have numbers here. We're just meant to think of this conceptually. And then also the amplitude is how long does it take to get back to the same position? How long does it take to make a whole revolution in its simple harmonic motion? Well, then that said, let's consider what colliding with block 2 is going to do for our amplitude and our velocity. First off, for a spring block system, we do actually know a relationship for amplitude, or not amplitude, I'm so sorry, period. We do actually know a relationship for our period. T is equal to 2 pi square root of m over k. K is the spring constant, m is the mass. But you can see here that, and it might even be a little bit easier if I write it like this, 2 pi root m over root k. It's the same thing, but I wrote it like this so that you can see that t is directly proportional with the square root of m. So if m increases, t is going to increase by some amount as well. So what's happening here is when block 1 sticks to block 2, we're essentially just increasing the mass of our oscillating object. So if we're going to increase the mass of our oscillating object, we're going to increase the period of its simple harmonic motion. That said, increasing the mass of an object, okay, increasing the mass of an object decreases how much acceleration it experiences for any given force due to Newton's second law. So Newton's second law is F equals ma. All right. If force is staying the same because the spring is staying the same, all right, and mass goes up, then the acceleration it feels from its restoring force is going to go down. And what that means is that it's going to be reaching smaller maximum velocities at equilibrium. So that's everything we need to know about how to draw this graph with the both masses stuck together. We know that the amplitude is going to drop because the max velocity is smaller, and we also know that the period is going to increase. So what's important that we do for this graph is we simply draw the graph such that it's not reaching as far away from the x-axis, and we're taking longer to hit our peaks and troughs. Now, what's important for this graph is that when we are drawing our graph, that our troughs are hitting on the same horizontal lines. This is not perfect, but make sure that it is actually simple harmonic motion, or you may not get a point for it simply being a sinusoidal curve. There are 3 points to get on this graph. There are 3 points. One of them is that the curve is simply sinusoidal, which we have here. The second one is that the amplitude of our drawn graph is shorter than the amplitude of the dotted graph that's already there. And then the third point is that the period is clearly longer. Okay, so you can see I'm hitting my peak here after the peak on the dotted line, and I'm hitting my peak here after the peak here. So it's taking longer to make a revolution. This is all 3 points for this graph. Okay, so that said, we have now hit the 1 point from our net force in this free body diagram, 3 points, okay, from answering our criticism of the student's statement, and then 3 points for drawing a graph when we have two masses. All right. If you have any questions about this topic, about this specific question, make sure you ask me. But this is a pretty common type of question, especially starting off with a free body diagram, moving on to a student statement that we have to critique, and then changing the scenario a little bit and analyzing what happens differently. All right, that's a pretty common set of asks that we get from the short answer question. All right, guys. That said, again, there's going to be 2 short answer questions for every FRQ, and they're typically a little bit easier than the experimental design and the other types of questions. But it's important that we grab all the points we can on these short answer questions because of the fact that they're a little bit easier usually. So make sure that you feel that you comprehend the steps that we went through on this problem, and I'll see you in the next problem. Good luck studying.